Good evening everybody, and thank you for the invitation to come and talk to Sheffield AS. The first of the two talks this evening, both of them relatively short half-hour talks. The first is called Just a Second, and as you can see from the subtitle, I'm going to be looking at what a second is, what can happen in 1 second, and the concept of leap seconds. So firstly, just let me throw a number at you. 61 million seconds, or just slightly shy of 62 million seconds. How long is that? How long does it seem? Can you judge what 61 million seconds is actually like? That number isn't just pulled out at random. That is the number of seconds since we went into lockdown in the UK in March 2020. It has been 61 million seconds since that happened. Whether it seems like more or seems like less depends on your perception of the lockdown, and it depends on your perception of what 1 second is. So in this talk I'm going to be looking at the definition of a second based on time and motion, how a second's defined. I'll take a little aside and remind ourselves just what can happen in 1 second, and then I'll look at the fact that the Earth is slowing down and ask why is that? And if the Earth is slowing down, does that mean seconds are getting longer? And I'll finish with what leap seconds are and why we appear to need them. So firstly, time and motion. How do we think about the passage of time? Well, ultimately, we always measure the passage of time by the motion of something, or at least something changing, quite often something moving. So of course in astronomy we're used to the idea of measuring the passage of time, for instance by the movement of the sun across the sky as indicated by a sundial, or as indicated by the changing phases of the moon if we want a slightly longer timescale. But if we ask ourselves what is a second, well surely that's trivial. We know what a second is. The Earth spins on its axis once a day, and a day is divided into 24 hours, and an hour is 60 minutes, and a minute is 60 seconds. So that means 1 second is simply 1 over that number, 24 times 60 times 60. Or if we write it out in full, 1 over 86,400. That's that fraction of a day. Simples. That number, by the way, 86,400, that's going to keep cropping up from time to time during this talk. So you could say, if that's the definition of a second, that fraction of a day, well, is that the end of the talk? Clearly not. I'm going to wrap it on for a few more seconds yet. So let's have a look at how the Earth actually moves. As the Earth moves around the sun, it moves in an ellipse. And that means, as you can see here, from the fact that the Earth sweeps out an equal area in equal time, so in other words, each of those two blue areas indicates a certain passage of time, in this case 1 month. When the Earth is closer to the sun, it moves faster. When the Earth is further away from the sun, it moves more slowly. So the Earth's speed around the sun varies, faster in January when it's closer, more slowly in the summer, in the northern summer. And that means, because the Earth is spinning at a particular rate, because it's going around the sun at a varying rate, it means the sun doesn't always appear to be in the same part of the sky at the same time of day. And that can be indicated by taking a picture of the sun at the same time of day throughout a year. In this particular case, somebody has taken a photograph of where the sun is, it looks like at local midday, and they've done that every week or two, perhaps every 10 days or so throughout the year. And the shape, this figure of 8 shape that is produced, is called an analemma. Now we understand the variation in the north-south, the altitude above the southern horizon, is due to the tilt of the Earth. If the Earth is tilted by about 23.5 degrees, then in the northern hemisphere during the summer, the tilt is towards the sun and the sun appears high in the sky. Whereas in the winter the sun would appear lower in the sky. In this particular case the photograph was taken, I believe, from Scandinavia, and hence the sun is rather low, close to the horizon in December, and very high in terms of altitude in June. But as well as that north-south variation, which is understandable just from the tilt of the Earth, you notice that the sun doesn't always lie on the meridian at local midday. Sometimes it arrives at the meridian early, sometimes it arrives a bit late. It can be up to 15 minutes either way, as indicated by this figure of 8. And that's because although the Earth turns at a roughly constant rate, its velocity around the Sun in the elliptical orbit varies, and hence the Sun doesn't always appear to be in the same place. And that is why sundials are sometimes off by up to 15 minutes, because the sundial doesn't take into account the fact that the Earth's orbit around the Sun is an ellipse. So we can't use a sundial to measure how fast the Earth is rotating because of this elliptical orbit. So if we want to measure the speed at which the Earth is spinning, we need something significantly more accurate than a sundial. And if we want to measure the length of the day, here I'm talking about not the interval between sunrise and sunset, I mean the length of the day in the sense of the length of time it takes the Earth to rotate once on its axis. So we need a much more accurate clock. For the last 50 years or so, we've had such clocks, atomic clocks. Since 1968, the definition of a second has been a very precise number. It is that many oscillations of a cesium atom. I'm not going to read it out. It's clearly about 9 billion and change oscillations. And that precise number is, if we count the number of oscillations of a cesium atom, that will give us 1 second. Strictly speaking, it's not the vibrations of the atom. What is measured are the microwave frequencies of microwave radiation being emitted and absorbed by the atom. But that's the same frequency. And it's not any old cesium atom, it's a particular isotope of cesium, cesium-133. So that has been the standard for time since the 1960s. It's called the cesium standard. And that's what an atomic clock used to look like. Now, an atomic clock ought to be good, if it's built correctly, to a precision of order 1 nanosecond per day, 1 billionth of a second per day. And over a period of time, that would be equivalent to something like a 1 second drift in time over 30 million years. And we can tell that by building lots of atomic clocks and checking them against each other. So atomic clocks used to be quite bulky, then they got down to about the size of a domestic fridge, and now it's possible to make an atomic clock about the size of a toaster. You can see here NASA are developing such an atomic clock. It's not the entire thing in front of these technicians, it's the little box that they're holding on to at the very top of this particular structure. The idea is that if you can make an atomic clock really small, you can put it on a space probe, and then that probe knows the time very accurately, which makes it easier for that probe to then navigate throughout the solar system. And here on Earth, time matters as well. It's not just a question of sending probes out to Jupiter, in which case we might need accurate time. We need accurate time here on Earth. If you think about the GPS system, the Global Positioning System, your position on Earth, as indicated by this little cartoon on the right, is worked out by calculating how far you are away from a bunch of satellites that you can see from your location. There are 25 satellites in the constellation, and you might be able to see 3, 4, 5, 6, 7, anything up to a dozen or so satellites at any given time. And by working out how far you are from each of those satellites, you can work out precisely where you are on the surface of the Earth. But given that these distances are calculated by timing, i.e. working out, knowing the speed of light, how long it takes the signal to get from the satellite to your location on Earth, you need atomic clocks on each of these satellites to keep accurate time. If you think of the speed of light being 300,000 kilometers per second, if one of those atomic clocks was wrong by 1 millisecond, then the distance you calculate to the satellite would be wrong by 300 kilometers. It wouldn't even necessarily put you on the right continent. If the atomic clocks were wrong by 1 microsecond, the distance could be wrong by 300 meters. Enough to put you in the right town, but rather difficult for navigation in terms of taking the next left turn, for instance, off the motorway. So you can see that accuracy definitely matters. The atomic clocks in the GPS system are hopefully good to a few nanoseconds, which gives us the accuracy in terms of positioning to a few meters. To keep everything synchronized, the GPS clocks on all of these satellites are resynchronized as often as possible, typically every few hours, to eliminate any possible drift. If for any reason they can't be resynchronized, the satellites onboard clocks should be good for quite a few days, possibly even a few weeks, before the accuracy with which you can position yourself starts to become a problem. But just to make sure drift is not a problem, they are resynchronized every few hours. In terms of earthly existence, let's just ask ourselves what can happen in 1 second. The fastest supercomputers can do quite a number of calculations per second. In red there is 200 billion. No, that's not the number. The number of calculations is not 200 billion. It's not even 200 trillion. It is 200,000 trillion calculations per second. That's what we mean by a supercomputer. These things are truly impressive in terms of the number of calculations that they can do each and every second that they are running. And even with a computer like that, running a simulation, for instance, of trying to work out what's going on in the early universe, how galaxies came to form, etc., those simulations that you might have seen the results from, those might take weeks or even months of number crunching on a computer like this. So 200,000 million calculations per second, it can still take months to do the sort of calculations that are necessary in astrophysics. An awful lot of calculations required. We are used to the idea as astronomers that light takes time to get to the nearest star or the next galaxy, etc. But remember that 300,000 kilometers per second is fast compared to anything that we can do in terms of, for instance, throwing objects around the solar system. The Voyager planetary probes that went to Jupiter, Saturn, Uranus and Neptune, well, they're travelling relative to the Sun at about 16 kilometers per second. Obviously a tiny velocity compared to the velocity of light. And if again we come down to some very mundane things and ask ourselves what can happen in 1 second, let's just have a think about what happens on the internet in 1 second. Here I've taken some statistics from pre-pandemic numbers. So this is what happened in 2019. In each and every second of 2019, 300,000 texts were sent between one person and another. There were something like 60,000 searches per second on a search engine such as Google. Other search engines are available. In 1 second, 75,000 videos were streamed each and every second of 2019. 75,000 videos, I think most of which involved cats. 700,000 messages via apps such as WhatsApp, for instance. And the most staggering statistic of all, the total number of emails sent every second was of order 3 million emails per second, every second. Now, we know that a few of those could easily be spam, but still, if you think about the amount of communication which is flying across the world each and every second, this was pre-pandemic. I'm sure 2020 and 2021, those numbers would be quite a bit higher. So that's what's happening on the Earth. But let's return to this idea of atomic clocks being accurate enough to be able to measure the rotation of the Earth. The atomic clocks that have been running for the last 50 years tell us that the Earth is slowing down. Back in 1968, when atomic time was instigated, the Earth made one turn relative to the Sun in 24 hours, 0 minutes and 0 seconds. In other words, precisely 86,400 seconds. The second was defined such that there were 86,400 of them in a day. And that meant that the day was 24 hours. But that was 50 years ago. Now we measure the rotation of the Earth and we find that the length of a day is now 86,400.001 seconds. It now takes a millisecond longer for the Earth to spin than it did 50 years ago. Why should that be? Well, we have to go back some 4.5 billion years to get the answer to that. It is thought that 4.5 billion years ago, An object, perhaps the size of Mars or so, impacted the very young Earth in a collision, and the spalled off material eventually condensed into what we now call the Moon, but that impact would have changed the rotation of the Earth. We've got no idea how quickly the Earth was spinning back in those days, because the impact of Theia would have completely changed that. Theia is simply the name we give to this object that is hypothesized to have crashed into the Earth. So it was a very disruptive experience. At that time, it is thought that the rotation of the Earth, once the impact had settled down, the rotation of the Earth was approximately one rotation in 5 hours. And over time, the spalled material would have condensed to what we now call the Moon. So the Earth was spinning very rapidly in those days, and ever since then it's been slowing down. Why is that? Well, that's because of the Moon. So we can see that here we have a cartoon of what's going on. The Moon on the right hand side here is raising tides on the Earth. None of this, of course, is to scale. So the Moon raises tides on the Earth, and as the Earth rotates, the tides, the high tides, get rotated a little such that the line joining the high tides doesn't quite point to the Moon. It gets dragged, the water gets dragged by the rotation of the Earth. So the Moon is actually pulling on this closest tidal bulge and is slowing it down. In a sense, the Moon is robbing the Earth of some of its angular momentum. So the Earth is slowing down and the Moon is getting further and further away and increasing its angular momentum. We're used to the idea that only one face of the Moon faces the Earth. Well, because of this effect of the Moon slowing down the Earth's rotation, eventually in the far, far distant future, the Earth's rotation will be so slow that one face of the Earth will always face the Moon, just like at the moment one face of the Moon always faces the Earth. In other words, there will be complete tidal locking. From one side of the Earth, people will be able to see the Moon all the time, clouds willing, and there will be one side of the Earth which will never be able to see the Moon. That's a long way in the future, but for the time being, the Moon is slowing the Earth's rotation, and it has been doing for 4.5 billion years. So the Earth's rotation might have been 5 hours a long time ago. It's now approximately 24 hours, and in the far future it'll be a lot longer than that. So who cares? The day is not an exact number of seconds anymore. It used to be exactly 86,400, now it's 86,400 and a bit. Who cares? Well, it's just like the problem we have with a year not being an exact number of days. And of course we're familiar with how we fix that. If a year is 365.2422 and other decimal places which I won't bother about here, we know that a year is a little more than 365 days. So if our calendar is 365 days, the calendar would get out of sync with the seasons and it would drift. So what do we do about that? Well, the easiest solution is to add an extra day every 4th year, a leap day into the year. That would produce an average year length of 365.25 days, which is close to the number in red, but still not quite right. We would still get a little bit of drift of our calendar relative to the seasons. So it was decided to skip a leap day in a century that's not divisible by 400. That sounds like a rather odd way of defining it, but that simply means that every 400 years there won't be 100 leap days inserted, as you would if you had one every 4 years. Every 400 years you have 97 leap days added. In other words, 100 minus the 3 for those years that are not divisible by 400. That gives you an average year of 365.2425. Note that that is very close to the actual year in terms of the number of days. So if we stick to this idea of adding leap days according to this formula, that will keep the calendar synchronized to the seasons for thousands of years into the future. So in other words, the calendar problem is fixed using leap days. Fine. But what about our clocks? If we want our 24-hour clocks to stay synchronized with the rotation of the Earth, In other words, when our watch says it's daytime, we want the sun to be in the sky. We don't want our watches to gradually desynchronize with the actual motion of the sun. So, do we need the equivalent of leap days added every once in a while? Leap seconds? Well, that is certainly one solution to keep our clocks synchronized with the Earth. If the Earth is slowing down, we add leap seconds every once in a while. Well, actually, we don't need to add leap seconds. We could keep the clock synchronized with the Earth if the Earth is slowing down, simply by slowing down our clocks. If we let seconds gradually get longer, then that will keep our clocks synchronized with the Earth. However, if we let seconds get longer, scientists would be absolutely furious, because it would mean that we would have to basically tell our atomic clocks to keep running slower and slower and slower as time goes by over many, many years. In other words, the definition of the second would keep changing, and scientists hate things where definitions keep changing. You want a definition, you want to stick to it. So letting seconds get longer is not a satisfactory solution. Let's have a look at how long a day has been in the last few years. Here in this graph, we're plotting the day length after subtracting 86,400 seconds. In other words, it's the bit left over. And the bit left over here is measured in milliseconds. So is the day longer by 1 or 2 or 3 or 4 milliseconds? And you see that it's varied over the last few decades, from the 1960s, when atomic time was introduced, up to this particular graph seems to go to 2019. So we'd see a number of things in here, one of which is we seem to have a whole load of spiky noise. Well, it's not strictly speaking noise, it's variations on a time scale. If you look at the little squares, which are each 1 year long, you notice that this variation is regularly once every year. And we think we understand that. Because the Earth tilts towards or away from the sun on an annual basis, as we go through summer and winter, that changes the amount of solar radiation in the northern hemisphere and the southern hemisphere. And that changes the way that the air circulates. The atmospheric circulation changes depending on where the heat is being dumped. Is it being dumped mainly on the land, or is it being dumped mainly over the sea? That depends on whether it's northern, summer or winter, because the land distribution isn't totally symmetric on the Earth. And the rotation of the atmosphere around the Earth, well, that carries a certain amount of angular momentum in itself. If you like, the atmosphere spins at a particular rate, and so if that changes, it changes the spin of the Earth. So we understand this variation from summer to winter to summer to winter. That's fair enough. But what about the elephant in the room? Why is the Earth's rotation speed, or rotation time, varying according to that red line? If we ignore all of the hair on top of that, all of the what looks like noise on top of that, why did the Earth get slower during the 1970s, and then speed up during the 1980s, and then slow down again, and then speed up again? What's going on? We don't think it's the atmosphere, because we know what that's doing. We don't think it's the Earth's crust, because yes, earthquakes can change the way the rock of the Earth is distributed, whether it's the continents or what's below the oceans. So yes, earthquakes can rearrange the Earth's crust, but that tends to produce rather small variations. What's producing this variation over many years or decades? I don't think that's really fully understood, but a lot of people seem to think it's to do with the way the Earth's mantle is moving. Not the core, not the crust, but the mantle in between. So that's an ongoing area of research. We know that leap days are inserted at a particular time. We're all familiar with the idea that if we need an extra leap day, we put it in every 4 years or so, and we put it in on the 29th of February. That's been agreed in the Gregorian calendar. But what about leap seconds? If we're going to put a leap second in to keep the clock synchronized rather than the calendar synchronized, what do we do about leap seconds? Well, that is decided by a body called the International Earth Rotation Service. I'd never heard of these guys before, but apparently they exist. I wonder sometimes what would happen if they ever go on strike. One assumes the Earth would still continue turning. But the Earth Rotation Service decide how often we need to put a leap second in and when they should be inserted, in which month, on which day. So if we go back to our graph, instead of looking at the grey line with all of the noise on it, let's look at the other grey line going from the bottom left to the top right. In 1972, that's when leap seconds were first introduced. Let me just move my camera over slightly so you can see the scale there. So leap seconds were first introduced in 1972, and they've been added according to this particular pattern. So you notice that during the 1970s, when the rotation of the Earth was quite slow, 86,400 seconds plus 3 milliseconds, so quite slow rotation, lots of leap seconds were required to make that correction. But for instance, during the noughties from 2000 to 2005, the Earth's rotational speed was very close to 1 rotation in 24 hours. And so for quite a few years here, no leap seconds were needed, and so no leap seconds were introduced into our clocks because they weren't necessary to keep the clocks synchronized with the Earth. If we are going to put a leap second in, what do the clocks actually look like? Well, you know what normally happens if you were to look at a clock close to midnight. Forgive me if you know exactly what that looks like, but I'll put it in the bottom right hand corner. As the clock approaches midnight, 58, 59, 0. The clock changes and you obviously kickstart a new day at 0, 0, 0. But if you need a leap second, what do? Well, the clock has to show a different time. So the clock would show what's shown here, 58, 59, 60, and then it goes to 0. In other words, 23, 59, 60 is a perfectly legitimate time. It doesn't happen that often, but every once in a while, perhaps every few years, the time of 23, 59, 60 is a valid time which fits in between 23, 59, 59 and the start of the next day. But if you are going to insert a clock at midnight, well, whose midnight are you going to use? Because everybody's midnight is different. Midnight in Japan is not the same as midnight in India, or midnight in Africa and Europe, or midnight in America. If you don't add a leap second at the same instant, if everybody puts a second in at their own local midnight, that means everybody's clocks are slightly out of sync with each other. Perhaps by only a second. Does that matter? Well, remember what can happen in 1 second. Millions of emails, thousands of messages, and how much money gets moved around the world by electronic transfer. You can imagine if clocks weren't synchronized, what sort of fraud could possibly take place in intercepting money that doesn't exist at point A and doesn't exist at point B because they haven't synchronized their clocks properly. Some people really don't like the idea of leap seconds, mainly because, unlike leap days, which are added according to a formula which is going to work for thousands of years, we don't know when the next leap second is going to be. We can only determine leap seconds by watching the rotation of the Earth and seeing if it's speeding up or slowing down, and then having the Earth Rotation Service decide whether or not we need a leap second. So you can't predict when they're going to be. But all computer systems need to be aware of them, because otherwise you can't calculate the difference between this time on this day and this time on that day. At least you can't calculate it accurately. Some computer systems really do not like leap seconds because you have to keep track of past leap seconds, and if we do introduce a leap second in the future, any new operating system has to be built to make sure it understands the existence of future leap seconds. Some computer systems will crash if you try and set the clock when a leap second is due. Some companies really do not like the idea of leap seconds. For instance, Google don't like the idea of 1 minute of the day having 61 seconds in it rather than 60 seconds. So they use a system called smearing to avoid the minute before midnight having 61 seconds in it. They add the leap second a few microseconds at a time continuously throughout the day. In other words, they deliberately run their clocks at the wrong speed. They run their clocks slightly slow for the entire day, such that by the end of the day they've made up that 1 leap second. That means Google's clocks are not synchronized with everybody else's clocks on a day when a leap second is going to be introduced. Imagine, just for a laugh, imagine what if we did that with the leap days. What if we smeared a leap day, not by adding February the 29th, but by running clocks slow during February, as in this cartoon? Why do the clocks say it's 3 a.m? The reply, well, adding an extra day creates too many glitches in February. Instead, we're running our clocks 3% slower during the whole of February to avoid the irregularity, i.e. on the 29th. So that's a joke. The idea that Google has expanded its idea of leap second smearing, which it does do, into the idea of leap days. Okay, leap day smearing is a joke, but the problem of what you do about leap seconds is serious. You can't let the clocks drift, or can you? Is it okay to let the clocks drift? Are you going to redefine the second? Not good for scientists. Or are you going to keep adding leap seconds once in a while on an ad hoc basis every few years as and when necessary? Well, the International Telecommunication Union is an agency that was tasked to think about this and consider whether or not we should continue to add leap seconds into time clocks, into time signals. In 2015, they came to a monumental decision. They decided not to decide anything until 2023. They simply procrastinated, which is a great way of dealing with the problem. Quite why they put it off till 2023, I don't know. But we're now in 2022 and it's not far away. Sooner or later, somebody is going to have to make a decision about what to do about leap seconds. Are we going to live with them forever, or are we going to find some other solution to synchronizing our clocks? So I've told you about time and motion, how time is only defined by looking at change or looking at motion. We know what the definition of a second is by atomic clocks. We know that a great deal can happen in 1 second, so it is starting to matter in this digital age. And we know that the Earth's rotation is slowing down, and we know why, because of the moon. The consequences, well, we either let seconds get longer or we add leap seconds. And whether we continue to do so, well, it sounds like that should be decided next year. Watch this space. Thank you for listening for the last 2,000 seconds.